This is about environmental sensing. So you can, with recent firmware updates to the Prime, there are primitives in there in PPL, so not necessarily in Python. You've got USB open, which returns a list of connected USB devices. I've said USB HID, but we'll come to that in a moment. Open with a vid and a PID, opens a specific device, returns a list of the input and output report lengths that you can send to and from the device. You've got USB send that sends one packet of USB data, and you've got USB receive, which returns a list of data items that have been received by the calculator. So you need these in order to start being able to interface the Prime to anything else. So the FT260, and that is a USB HID, so device, hardware interface device, sorry, I beg your pardon, I've lost it already. Human interface device. Human interface devices are a class of USB device that are designed to be able to plug in almost driverless-ish, sort of, maybe. So it includes things like keyboards and mice and game controllers and that sort of stuff. The FT260 is a little board, and it's on this little circuit, on this breadboard. The FT260 is actually the chip in the middle, and the rest of the stuff around it, the blue board at the top there, is turning it into an evaluation board. So I've got jumpers, so I can decide whether it's bus powered or externally powered. It's got all of the pinouts, basically, because I can't solder onto something that is, well, 5mm square, because I can't see it. The default I2C configuration that this thing provides, it's got an I2C and a UART. The I2C configuration is usable as it is. The default configuration for the UART is 19.2K, no stop bits, 8 data bits and 1 stop bit. No parity, 8 bits, 1 stop bit. So I think that makes it compatible, although I haven't tried it yet, with the HP50, because I haven't got an HP50 serial lead. But it is not compatible with the 48s because they only go up to 9.6K. Yeah. The Prime firmware limitations mean that you need to send a different type of USB message to it in order to alter the config, and that is not implemented in the Prime firmware yet. So we can hope that they will do it. If you want to buy that the blue board, the evaluation board, it's $15 US, £12.66 plus postage and packing from Farnell. So it's a reasonably cheap little device. So once you've got that, you've got something that the Prime can talk to. It can send information to and from it. The Bosch BME 680 is this little thing at the top here. That is a low power gas, temperature, barometric pressure and humidity sensor. Its uses, according to Bosch, include things like indoor air quality monitoring, weather forecasting, temperature and humidity alerts and all the rest of it. And the chip is this, if you can see it, I know it's tiny, but it's the silver bit in the middle. So it is 3mm by 3mm. It's designed for people like Samsung or Apple to stick inside on the circuit board of a mobile phone or something along those lines. The board that I've got is from Pi Minori, the Raspberry Pi people, and again, so about $20 US, £16 from Farnell, you can purchase one of those. This has, okay, so it's going to measure 4 things: gas, resistance, temperature, barometric pressure and humidity. It has a 53-page manual which includes pseudocode. The registers that are used, so it's got a 256-byte memory map with calibration parameters that were set on the production line at Bosch, and fixed values that you read, parameters that you set, and then you read these 4 different measurements out in chunks of 8 bits or 4 bits, and then you glue them all together. There is also a GitHub repository with sample C, and I read the manual repeatedly and I couldn't get the damn thing to work. I was getting all sorts of I was getting 10,000 out of it for the barometric pressure, when we know it's going to be about 1,000, yeah, and that sort of stuff. And it said it was 46 degrees C in my lounge or something like that. So I had a lot of aggro trying to get the code on this to work. Somewhat annoyingly, I put a disclaimer on the front. Some of this work was originally done by somebody who posted some routines on the Museum of HP Calculators forum, but he posted really awful, intentionally de-resed pictures of it working and incomplete source code. And when I asked, because everybody on there publishes the code, he said, I can't give you it, and I don't know why. So it's taken me on and off in my spare time, best part of a year, to get it to the point that he'd got it to, and she had evidently got guidance, I suspect, from Cyril as to how to actually make this work, because the low level stuff, the talking to the I2C, is quite, it's bit manipulations over USB, so it's quite tricky. What was particularly interesting, and why my version didn't work to start with, is because in the 53-page manual it absolutely completely failed to tell you that some of the 256 bytes that were in the memory map are signed and some of them are unsigned, which is really handy, isn't it? So I literally had to read every line of C, and more on that later. So this is Mark's modified memory map. These are parameters that you set, calibration parameters that you read, or results that you come back. So this is my enhanced version, because the one in the 53-page manual had about 16 entries in it. As you can see, the actual chip is a lot more complicated than that. To connect it to the FT260, this silver bit that you can see at the top, just about there, that's micro USB to micro USB. So you might have one of those, so it's an OTG cable, it's called on the go cable. Revision A primes did actually come with one of those, but it was incredibly long, so you might want to spend a couple of quid on eBay buying a short one like this. You use 4 wires, so the 3.3 volts goes from the FT260 to the BME 680, ground goes to ground, and then once you work through the manual, you work out that the clock is on IO0 and the data line is on IO1. You don't need any jumper changes, you don't need a power supply or anything in order to make this work. So my software is built on a bit of sample code that did the I2C bit, plus Bosch's modified C code. When I was reading it, I was a bit puzzled as to why Bosch took these values out of a 256 byte array, basically, and used in C an associative array to look up the values. And I wondered why that was, and it transpires that there is another version of the chip called the BME 688, which when I plugged that in, because I've got one of those as well, I thought, and it said it's compatible with this. Yeah, it's compatible, but every byte is in a different location. So, which is why they stored it in an associative array, so that which had I realised that before I started, I would have stored it in an associative array, as opposed to the array that I did store it in, but never mind. I have developed the Prime GUI for it. So we have here BME 680 GUI, which talks to the device and draws in real time. You should just be able to see that starting off, but you will see the graphs coming in. So it's taking a sample with a delay about every second, and it's giving you the temperature, which it says is about 21 degrees. It's 115.5 HPA, hectopascals. The relative humidity, because I've got my finger near it, is about 54. the gas resistance is in kiloohms. This is a proxy for air quality. So there is a heater that I'm heating up for every sample to 300 degrees C for 0.01 of a second, and then reading the resistance across it. That's a proxy for air quality, and you'll see that the graph bottom right is gradually building up, and these graphs I've got them auto scale. So it started off at 20k when I turned it on, and it's up to 43.
Does your gas quality correct for the change in pressure?
It corrects for there are things in there that change for adjust for temperature and pressure. Not pressure. No.
Well, all I would say is if you heat up a water and see how its resistance changes, that's been the major effect with the pressure.
No, Bosch's algorithm, which I implemented, adjusts for temperature, but I don't think I can't remember. We'll look in the 53-page manual afterwards. So these auto scale. And you can see, and they're gradually adjusting their values. Yeah. The interesting thing with this is, so I finished writing the code while I was on holiday, like you do, in the Cotswolds, in a little cottage in a village. And when we went into this cottage, the first thing that we noticed as we opened the door was the smell of the oil-fired boiler. And we opened the downstairs utility room, and there's the loo, and there's an oil-fired boiler in there, and it was very hot. So even though it was the middle of summer, of course it's heating the hot water, and it was very smelly. You know, it was very obvious to us. The gas, you're familiar with gas boiler, oil-fired boilers. It was very noticeable, and I thought this would be a great test for my air quality measurement. So I left this running, plugged into the Prime, doing its graph for about 3 hours when we went out, getting samples every second. The Prime will do that, its battery's good enough, despite the fact that it's powering a heater in that board. And I left it, and it came out at a certain number. Now, in kiloohms. The thing is a lower number means worse air quality. Yeah, so it eventually settled, I think, at about 150 kiloohms while it was in the utility room with the door closed, with the oil-powered boiler making a horrible smell. So 150 kiloohms. The cottage had the kitchen that side, the opposite side of the stairs was the lounge, upstairs was the children's bedroom above the smelly boiler, and our bedroom and the bathroom was the other side. So I then thought, well, just as a matter of interest, we had the windows open because it was the middle of summer. I left it running for 3 hours in our bedroom to see how much of this noxious stuff was being transmitted to our bedroom. So what do we think? Do we think the air quality was better or worse in our bedroom? Bear in mind we had the windows open, and we were on the opposite end of the house to the oil-powered boiler.
Bus stop.
No.
Pollen.
No. It doesn't measure pollen. It's not particulates it measures. It's air resistance.
And resistance is made worse by the
It was in the Cotswolds, so it's a reasonably clean area of the country.
One would have assumed that your bedroom would have been a better place, but
yeah.
by a basis of your question, it's probably
the fact that I'm asking the question, and what we think is, so because I've been chatting to the people at the university about this, and this is a common thing, the paint on the walls, the carpet's decaying, the fabric on the bed, and all of that sort of stuff makes an impact. So actually the air quality was worse in our bedroom than it was in the boiler room.
Really?
Which is staggering, isn't it?
How are you finding air quality?
Well,
Exactly.
according to Bosch's, this sensor is designed to measure indoor. Well, it's air resistance.
It's much easier.
It's air resistance.
It is not measuring the DC resistance of air. It's not going to bring it over to.
No. It's got a.
Yeah.
There's a piece of metal in the sensor in front of the sensor.
To make measurements and to know what you're measuring.
Yeah.
Which appears to be what's happening.
So what I unfortunately forgot to do, by the looks of it, is I emptied my bag of my lecturer stuff, which is a bit annoying. So what I'll have to do instead is I will show you, if you can see the graphs.
That's quite clear, actually.
Yeah.
so you won't see it up there, but you'll see the graphs will auto scale, and you can see I've sent hot breath into it, and it's less obvious. What I do normally, I forgot to do it, unless there's one in here, I take a pen off a whiteboard marker and the air quality, and hold it near it, and the air quality absolutely falls off a cliff, and that's one marker pen in the same vicinity as the temperature sensor. So
finding something.
Oh yeah, yeah.
The normal way,
and you can see. Can you see the changes in the graphs? You can see the spike from me breathing on it, and you can see the barometric pressure stayed exactly the same as it would do. The air resistance has a glitch, which was me breathing on it, and the humidity went through the roof. So it went from 43% up to 74% as I breathed on it. So all pretty cool. And there is, and when you exit it, the program, it turns off. But the program returns a matrix, which you can then, which contains the time and date of the samples, and the four results, and then you can feed that into the spreadsheet, or you can download it to your PC and manipulate it in Excel or whatever, and that sort of stuff.
Perfect for use in education.
Perfect for use in education, which is exactly what I've been doing with it. There's also a terminal version which just displays it on the console, but that's obviously less pretty. So, to get to that point took me about 1,100 lines of code. So maybe a couple of hundred of that were the USB to I2C code that I reused. There was a bug in it that I had to fix that the guy who wrote it originally hadn't spotted. So next stage was, well, what sensors shall we plug it? And just for a comparison, I made the clone of Outrun a few years ago, and that's more lines of code to read that sensor than there is for the Outrun game. So it's not a minor undertaking. We bought, daughter and I bought time of flight sensors because we're interested in looking down ducts to see where the blockages were, weren't we? So a VL53L3CX, and this is a bit like an ultrasonic sensor in that you send a beam out and it comes back and you measure it, but this one is LED laser, if that's the correct term. Yeah. So I thought, one measurement, that'll be easy. We've done most of the work, and it's not. It's actually an array of sensors, and you have to ignore the sensors that they have determined were faulty at manufacture. You have to use the other ones. You then have to process them. There is more code to read distance to object out of the top of the LED than there is to do everything that I've just shown you. So as yet, that's the project for next year. So if you're interested in doing this and reproducing it yourself, my suggestion is that before you go and purchase said sensor, you read the API and the sample code and the manuals before you start, and then work out how hard it might be. So,
I mean, your time of flight is about 6 months then?
Yeah, at least 6 months, yeah. So taking my own advice, I found the Analog Devices ADXL343, which is a 3-axis configurable range digital micro electromechanical accelerometer. In other words, it's got a weight inside it that moves in response to acceleration. The spec sheet says that it can be used for things including activity and inactivity sensing, so turning the display off on your device if it thinks that nobody's using it, nobody's touching it. It can be used to detect single and double tap detection in any direction, X, Y or Z. Free fall sensing, so you could put it in a laptop and it could park the hard drive if it thinks it's just been knocked off the desk. And stuff like that. Unfortunately, I think most of those features you will not be able to use on the Prime. I haven't got around to trying that yet, because they require the use of interrupts, and interrupts are not supported in the Prime firmware at the moment. They say the uses include handsets, gaming and pointing devices, hard disk drive protection and all the rest of it. It is the red board on this circuit board that's attached. So the actual chip is 3x5x1. Again, I can't solder that fine. So you buy it on an evaluation board, which is what the red board is, for about £6. It has a somewhat depressingly 37-page learning guide and 35-page data sheet. But I wrote 12 new lines of code to make this work, and it works, which is very nice. So I will demonstrate this to you. This will be an interesting one here.
12 new lines of code. That's on top of the 1100.
That's on top of the 1100 that I wrote before. So you should be able to see on there. Can you see? So if I tilt it round, can you see the trace? Yeah. And that's the tilt sensor, which is on the board. Yeah.
Is that 3-axis?
It's yes, but my display is not 3-dimensional, and I would have to stand up and down very quickly in order to get it to work. But yes, it is.
Yeah, same as the phone.
Yeah, same as the phone. So you can see what it's doing there.
And what chip is that?
That's this ADXL343.
In the heading.
In the heading, up at the top, in the big.
No, I know that. I mean, on the board, you've got 3 chips, therefore on the board.
Yeah.
Okay.
The red one down at the bottom with the LED next to it.
Okay.
Yeah, which handily tells me that the board is powered up as well, which is quite handy. But which, if you were worried about flattening your Prime battery, you might want to snip the wire on the LED. So, again, connecting it, very straightforward. USB to USB OTGA cable to the Prime, to the FT260, and then 4 wires, 3.3 volts, ground, clock and data. No jumper changes whatsoever, no resistors, capacitors or anything else, because they're all on the evaluation board. They're all done for you, so you're literally connected. And I2C is a bus, so you literally parallel these if you want 2 sensors running at the same time, which is what I've done on my breadboard. So you might just be able to see the wires on there are connected one after the other. Okay, so we've got an accelerometer. So I thought, well, what can we do with that? So first reasoning was, I know, I'll take the car out to the roundabout at the end of the road, which is quite big, and see what maximum G I can get going round the roundabout. But I thought,
I remembered it was a Saab.
yeah, so it's got rear wheel steering, so it can actually go round bends very quickly. So I built a tilt library. So the realisation suddenly dawned on me, and I need to go back and re-engineer my code, that you can actually have libraries, and its support on the Prime in PPL, and it supports C-style, scope. So I can have a tilt library, and so I wrote a tilt library, checks if the FT260 and the accelerometer are connected, sets, sorry about this, think C, yeah, global flag, tilt enabled to true, and then tilt read returns X, Y and Z, each in the range of -1 to +1, and tilt invert if I want to hold my thing upside down or back to front or whatever. They're just there to swap the values around to make it easy to use. So you can add, you can call the tilt library on any program where tilt sensing might be useful to you. Now then,
why in the range -1?
It's because when you get
one of them will always be about 1.
One, yes, Z is always 1 because it's got gravity on it. But I picked that range to make it easy because for applications to use. So it's tilt sensing, not accelerometer sensing, if you see what I mean. So if you wanted to tweak it, you could have the true accelerometer values, and pick the range that you want to return. But I can't simulate 16G on much, so it's a bit useless to me. So, If you would like to lend me your Prime, I will try dropping it off a table.
Yeah.
So the thing is, what can you do with a tilt library? Well, I'm pleased to say that after HPCC 2021, was it, that I presented this at? I finally got round to updating the racer to version 40 with increased draw depth, so you can see the green lines go further into the distance, which you can do on a G2 because it's fast enough. And you'll notice that when I started, rather than it saying press the keys, I now drive my car, it comes up with tilt to turn, and I drive my car by steering it from left to right, very badly, using the tilt sensor. Yeah?
That's very good, very good.
So just as a laugh, as a demonstration, it's good for the kids, isn't it? And you've got the very impressive tilt draw depth as well, so you can see the horizon a bit better than on the original version. So let me just try and stop that. And the thing is, my daughter over here is a bit of a whiz with 3D design. Hey Rose. So here on Bruce's one is a new Prime case where it works just like, there you go, tilt to turn. So you've got, and it works like the breadboard. So this is built, here's one I prepared earlier, here's prototype number 3. So Rose designed me the case, which has HP. We thought about putting MP and RP in it, didn't we? But anyway, we decided HP would fit. So it's got the HP logo in. The printed circuit board is, you can buy off eBay for a couple of pounds. You literally lift and shift off a real breadboard and solder the components on. So I've soldered the components on. You might be wondering why the temperature sensor is on the end of the wire. Well, there are things called grove or seed connectors, and what I'm thinking is that when we finish playing with it, is that we put a cover over this, and then we put a row of connectors on the back, and then you will be able to attach your sensors and potentially connect multiple temperature sensors. So you could have one inside a fume cupboard and one outside a fume cupboard, for example. The sensors, if you solder across these 2 pins on the back of it, it acquires a different address on the bus. So you could connect 2 sensors up. So you could hex 76 and hex 77. You would have 2 sensors, and then you could do comparisons between in and out of the sensors. And you literally screw the board on, and it's in the case, and then you can. The tilt sensor is built into the case, and it will. It's like without the. Yeah, no.
The screen's facing.
I know. I can't do it by foot. But the idea is that it looks like an HP Prime, and then when you want to use it, you turn it over. We've got to solve the issue of how we get the wire to be nicer, but we'll get around that.
Right angle connector.
A pair of right angle connectors and a very short wire. Yeah. So there we go. So you have FT260 with I2C, I2C sensors. Take care with your choice of sensors. It's very simple to wire up. Before I finished this talk at HHC, a gentleman had already ordered all of the component parts for this, and he came to me afterwards and said, "This is fantastic. I'm going to use it on a machine that's spinning." He's going to put the accelerometer on a machine that is basically a lathe, so that he knows when the piece that he's machining is perfect, because he will be able to see from the accelerometer whether the machine is vibrating, because the piece is not yet finished. It's dead simple to wire up. You'd need a Prime G2. Go and purchase them now. Is this a good reason to purchase a G2? Possibly. Unlike some of the experiments that you will see on the HP Museum site, where people are doing other things with these, that what they've tended to do is they've attached something to an Arduino and then programmed the Arduino and then talked USB to the Prime. All of the code sits on the Prime. So I will refactor the code now that the panic of getting it ready for the state. We were literally printing that case 48 hours before the flight. So once that's done, but it's my intention, unless Klaus makes me an offer that I can't refuse, to open source the software. And if everybody's got the software, then everybody can build, add additional drivers for different sensors, and then we will have an educational device, which is what HP want to turn the Prime into, with a variety of sensors at relatively low cost. So there we go. Thank you very much. Any questions?
One question. So you said no Arduino code. So it's not even anything to just do a straight pass through of the I2C up to the USB. How does
Nothing.
that work?
It is entirely code. I can show you the code. It's literally entirely on the Prime.
Right.
Yeah.
Okay.
Yeah. No, literally, you talk USB, you send messages on the USB that are I2C messages, and the 260 picks them up, says, oh, they're for me, and sends them out. One of the things I'm thinking about is that when you're using this, you can't connect it to your PC. And what I'm thinking is that maybe we've got enough room in here to put a hub in, and have a hub so that you can have a connector so that you can plug your PC in, and connect to the I2C devices as well. But then you're into, is there enough power in the Prime, which means then changing the jumpers on the board, and maybe putting a battery inside the case, or adding bus power from the hub, and then Prime power to the device or something like that. So it's a bit more complicated, and it depends on the loading. But like I say, I've managed to get it to run. I ran it for 3 or 4 hours with the sensor, which is power hungry, and the battery hadn't moved on the Prime. So and the display's on. I mean, it's dimmed, but it's on. Yeah. So because there's no way that I've found of turning the display off from a running program. So yeah.
So you literally 3D printed the case.
Yeah, Rose designed the case based on the original. So we measured the original case with where the grooves are. That was the hard bit, getting the grooves. This one actually, this was printed on the university's £150,000 3D printer, which is usually used for printing fleshy body parts.
If you actually have one of those at home.
No. Funnily enough. And the finish is stunning, but somehow or other it managed to just not quite get the grooves that hold the Prime. They're just too far apart, and you put it in and it fell through. So the night before I flew to Orlando, I was running a line of epoxy resin along the grooves and then filing it to make sure that it fitted. The one that Rose did on her £6,000 printer at work fits perfectly. So different material, different printer, there's variations. So we've got to work that out. But the case, because we printed it as a solid piece, this is printed in PLA with, is that right? PLA with PVA support. So what the printer did was it printed PVA, the HP badge in PVA, and then edging around the side to make the curves. It prints that in PVA glue. Yeah. The upshot of which is you sort of get little drag lines where the glue's gone from one place to another on the case, so it's not quite perfect. And then the PLA is printed over the top of that, and then when it's finished, she puts it in a washer, and the PVA washes away after 6 hours or something like that. About this one, I need to find out from Mia what material she used, but this is This has got a different support material to hold the structure together, which requires a chemical to remove it, but it gives an immaculate finish. And the finish that you're seeing on this case is the poor side. Yeah, bizarrely, because of the way it's printed, the good side is the side that's inside. So if you printed it that way, it would be fine, but you'd need over £100 of support material to hold it up while you're making it. So this cost me about £40 to print. So there you go.
So, a couple of good questions.
Yeah.
You mentioned the I2C command library.
Yeah.
I assume there's a way to send an arbitrary byte to an arbitrary I2C address.
Yes.
Yes. I mean,
but not built in. That's what the code is that we had to use. Yeah.
that strikes me as the obvious thing you'd want to do.
Yeah. Yeah. Absolutely. So.
I don't believe your two addresses for that sensor are adjacent, because the least thing is my I2C address, whether it's read or write.
Well, it depends.
Depending on what you use your convention.
Yeah.
There's two conventions.
There are two, I agree with that.
They're equally commonly used.
Yeah.
You either take top 7 bits or you take the whole. Yeah. The other thing, I really want to know what this Bosch sensor measures for gas quality.
Well, read the 64-page manual or 53-page manual.
I mean, the normal. I suspect that sensor was originally developed for car environmental control. Because Bosch very much in the automotive market.
It describes it for indoor air quality.
I mean, I would think climate control, if it was one of the original uses for it.
It could well be. Could well be.
That's what Bosch are known for.
Yeah, it could well be. You're right. Yeah, and turning the auto recirculation on.
Yeah, I mean,
things like that.
A car climate control system.
Yeah, yeah.
But I mean, a normal method of doing it is to have a catalyst on your heater.
Yes.
And you heat it up. Does it react with the stuff in the air? If so, it'll cool the wire more than it should do.
Yeah.
But I'd love to know exactly what it's measuring.
Is that in the manual?
Well, it's measuring.
It was describing it like that.
It's in the manual. Is it like we can look at it? Yeah.
So it says it's measuring the absorption of the chemicals in the air on the wire, on the coating of the wire. So that seems to match what you're describing.
Yeah.
But it won't be. It'll depend on the chemical. It'll depend on the pressure and on all the things.
So I apologise to all software engineers. There are more magic numbers in this code than you can shake a stick at. I will get around to fixing it. But there's some stuff to just basically get USB to send and receive properly. The guy that wrote this bit did put logging in it. So there is some stuff in there. And interestingly, there's code. It says in there, look, he's called. It was clearly part of an app, but he didn't publish the app, and it's called Data Streamer. So I wonder whether he's actually developing it for Moravia.
Actually, HP did actually start a development for Data Streamer.
Yeah.
So maybe he was working.
Maybe.
Yeah.
So if you look, talking to the FT260, you call USB open and you send it. The vid and the PID or whatever it is, and then there's a load of stuff with I2C send, which is a load of bit twiddling in order to convert it and read, and then there's some timeouts. He'd put some code in there which allows you to peak multiple registers, but then if we get down to the Bosch, the code that I implemented, so that the terminal version of the code. Here we go. Calculate gas weight. Calculate heat. The resistance that you need to send. Is that send? Yes. Send to the heater in it, and you can see there are all. I literally lifted and shifted the source code, the pseudo code. From the Bosch code, and you can see there is a lot of it, and I mean it's all just bit twiddling, creating a 20-bit number out of.
Oh, you don't have shifts in this language.
Oh, you do, but I use them in places, but it's just easier some of the time because it saves you faffing about. So there's quite a lot of code in. Here we go. This is reading the calibration data out of, and this is what finally, when I realised the bit about the signed and unsigned, was I ran this using a public Python library on a Raspberry Pi, and some of these parameters came out as negative numbers, and I thought, how can that number be negative? Oh, because it's signed. And then and you can see I've got fixed 8-bit signed and 16-bit signed and all the rest of it. So I do need to. It calls one method to get all 256 registers out of the Bosch device simultaneously. I use my trick, Bruce, of taking the first element off the array and putting it on the end, and then it becomes index 0, and then I can go into C programmer mode, and I'm happy. So I haven't got to add +1 to every single one of these magic numbers. But you read all of that lot, and then a load of those are used. But in terms of this is how you run it. So you set the parameters. You set the register on device 76, which is what it answers to run a gas measurement, single measurement once, 150 millisecond for the timer goes into that register. So that goes into register 71, into register 64 in hex. You send the gas resistance time. You set target temperature. You set filtering. You set I want humidity, temperature, pressure, and go and do it. Set that, and then you wait for the result to come back, and you process it, and that's how you get it back. So lots of code, but it like I say, it needs a bit of a tidy up and libraryifying, I think, and then it'll be all good.
Do you need to calibrate each device separately?
It is calibrated at the factory. Right. You can't alter the values that are set at the factory, but you could calibrate the values that you are using in your code afterwards.
Mm-hmm.
Yeah.
As a first approximation.
As a first approximation. Yeah. And there is actually a shortcut in there that whichever one it is that is dependent upon temperature, it could read the temperature and use that as part of the calibration for the next bit, because it's dependent upon the ambient temperature. But then once you've done it, it's fixed for that period that you're using it. Well, in actual fact, their code and the Raspberry Pi code and the source code didn't do that. They just assumed that you were going to use it where it was 20 degrees C. So it's hard code, which is close enough for most of us.
20C is normally taken as a nominal point.
Yeah, exactly. Yeah, and the difference that it's going to make is in the 8th digit or some significant digit, which I'm reading it out to 4 significant places, and that's about it.
HPCC to help you debug this?
I did indeed use an HPCC to help me debug this. But the Prime's got good base conversions and a base mode actually.
I would do this project just to use my HP16.
Yeah. So there we go.
That's what I used to use it for when I bought it actually all those years ago.
So if anybody's interested in what we
to make one of these.
I want Klaus at Moravia to see this.
Are you going to publish some of the stuff so we can get started?
The slides, the presentation. Yeah. Eric, it was I gave it last week at Orlando, so in Orlando.
Good.
But
very interesting.
Like I say, my intention is that we open source the software.
Yeah.
So that other people can write drivers for other devices.
For education.
But then my university, having sort of loaned me the time on the £150,000 3D printer, said, well, because that's in the business development unit, they said, well, can we develop it? But we'll see what happens with the case. So there we go.
Very good.